A cosmic flash, brighter than the sun, but it's over in less than a blink. That's a fast radio burst, a signal from deep space. It's become one of astronomy's biggest puzzles. A single blip found in old data. It rewrote our map of the universe's most violent events. These bursts were almost dismissed as interference from kitchen appliances. Then a repeating signal changed everything. What kind of cosmic engine does that? Concentrates that much power into a millisecond. The story of these bursts is a detective tale. It spans galaxies, human curiosity, pitted against the universe's greatest secrets. What's waiting for us in that cosmic static? It was a ghost in the machine. That first burst, it came from old data, a recording from 2001, the Parkes telescope in Australia. This big dish listening to stars, it had picked it up years before, and no one saw it. Duncan Lorimer and his student David Narkevic, they were going through old tapes, looking for pulsars, that steady heartbeat, and they found this spike. This scream, it lasted 5 milliseconds, and in that time, it had the power of 500 million suns. Then it was gone, the Lorimer Burst. That power meant it came from outside our galaxy, from a distance that's hard to even picture. The reaction wasn't excitement, it was doubt, a signal that strong, that fast. Could it be real? So they looked for interference, a satellite, an electronics glitch. Someone using a microwave, the usual things, but all the checks were clean, and that left a puzzle, a fingerprint with no hand, a shout with no source. It was so strange, so one of a kind, that for years people thought it might be a fluke, a 1 in a billion error, but a door was open now, a crack, and the question was there. Were we the only ones who heard that shout, or was the cosmos full of voices we just didn't know how to hear? They called it a fast radio burst. The name tells you the basics. It's fast, a flash of radio waves that's over in less than a blink, and it's a burst, an explosion of energy. In that sliver of a second, it can outshine our entire sun for days. Our sun is a continuous furnace. This is a camera flash, a strobe light so bright you see it from another galaxy. But how do we know it's from another galaxy? That's in the shape of the signal. Every burst arrives stretched out. The high notes get here first. The lower, deeper tones come in just a fraction later. That delay has a name, the dispersion measure. You can think of it like sound moving through water. Your voice gets distorted. The different frequencies travel at different speeds. Space isn't empty, it's filled with a thin haze of electrons. They act like the water for these radio waves. The longer the journey, the more electrons the signal passes through. The more stretched out it becomes. By measuring that stretch, that delay, astronomers can calculate how much stuff the signal passed through, and from that, they can estimate the distance. These bursts are not from our neighborhood. They come from billions of light years away. Their messages are warped by an ocean of gas, so we have a what? A millisecond blast of unbelievable power, and we have a where, somewhere far beyond the Milky Way. But that description creates a deeper question. What in the universe can do that? What natural engine can concentrate the energy of a star's lifetime into a pulse shorter than a snap of your fingers? From the beginning, fast radio bursts weren't just a mystery. They were a challenge, a direct confrontation with our understanding of physics. Skepticism took over. A one-time event could just be a fluke, a glitch. The universe is noisy, and our instruments are sensitive. The real question was whether the Lorimer Burst came from space or from us. Could it be interference? A satellite, something from a military radar. The simplest answer was usually the right one, and for a while, it looked like the skeptics had it right. That same telescope, Parkes, started finding more bursts, but something wasn't right. They looked similar, but their fingerprints were wrong. They had that dispersion, that stretch, but it was too small. It meant they hadn't traveled through much interstellar gas at all. That pointed to an origin not far away in the cosmos, but right here in our own atmosphere. Astronomers called these false signals perytons. In myth, a peryton is a winged stag that casts a man's shadow, a good name for a signal that looks cosmic but is really from Earth. For years, perytons confused everything. Every time someone found a new burst, they had to ask, is this real or is it another peryton? It cast doubt over the whole field. If some bursts were local, maybe all of them were. The search for a source became a search for the source of the noise, a slow process of elimination. Checking every device, every plane, every possible human signal that could fool the telescope, the answer came in 2015. A team at Parkes put in a new, real-time monitor. And they waited. When the next peryton showed up, the system traced it not to a point in the sky, but to a specific time of day. It always happened at lunch. The cause was, of all things, the staff microwave. If you opened the door before the timer ended, it let out a short, powerful radio pulse. The telescope's big dish, pointed at the horizon, would catch the reflection of that pulse off a nearby hill. It looked exactly like a signal from deep space. The mystery was solved in a way that was almost funny. The mythical peryton was a microwave oven. This is more than a good story. It shows a basic truth in astronomy. The hardest work is often telling the cosmic signal from the earthly noise. It takes a kind of careful detective work. You have to rule out every ordinary explanation before you can accept the extraordinary one. The peryton episode was a necessary trial. It made the field develop stricter standards, better filters. It made the evidence for real fast radio bursts, once they were confirmed, much stronger. The ghosts had been named. Now the search for the real voices could really begin. The universe has plenty of things that happen just once, but a pattern, that's something else. For a long time, every fast radio burst was a single flash. One brilliant moment, and then it was gone forever. It was like hearing a single word shouted from a crowd, and then silence. You could never find who said it. That made them almost impossible to study. A one-time event could be anything: a star exploding, two dense objects crashing together, any theory where the ending is final and catastrophic. Without a second act, the mystery just stayed frozen. Then in 2016, that changed. A team was using the Arecibo telescope in Puerto Rico. They were watching a patch of sky, looking at a signal first seen in data from November 2, 2012. It got a catalog number, FRB 121102. And it did something no one had seen. It burst again, and then it burst again. This wasn't a one-time cosmic scream. This was a source that kept talking. They called it the repeater. That discovery shifted everything. A repeating source immediately ruled out any explanation that required total destruction. You can't blow something up twice. Whatever was making these bursts was surviving them. It was an engine that could fire again and again. So the question changed. It went from what died to what is alive. What kind of object has that kind of resilient power? And a repeater gave astronomers a fixed address. Because it came back, they could point other telescopes at that one precise point in the sky. The world's most powerful eyes just waiting. They did that. Using a network of observatories, they finally pinpointed where the repeater lived. It wasn't in a grand spiral galaxy like ours. It was in a small, faint dwarf galaxy, more than 3 billion light-years away. That location was itself a clue. Dwarf galaxies are often thought of as cosmic building blocks. Places where conditions can be more extreme, more primordial. That this incredibly powerful object lived in such a modest neighborhood was another surprise. With a host galaxy identified, the repeater stopped being just a signal. It became a place, a laboratory. Astronomers could study the environment around it. Measure the galaxy's chemistry, look for other unusual objects nearby. This one discovery shattered dozens of the early, simpler theories. It opened the door to a new era. Now the hunt wasn't just for more bursts, it was for understanding the machine that makes them. The universe had given us a return address. The next step was to figure out who or what lived there. Pinpointing a flash from a galaxy billions of light years away, it's a problem of scale. A single radio telescope, no matter how big, just sees a blurry patch. It's like trying to read a street sign from a mile away. You know it's there, but you can't make out the letters. To see the details, you need a bigger eye. So astronomers built a virtual one, a telescope the size of the planet. The technique is called interferometry. You link radio dishes across continents: Europe, Asia, the Americas. They all stare at the same point in the sky at the same exact moment. And by combining their signals using the precise timing of when each dish gets the wave, supercomputers can stitch the data together. You get a single virtual instrument. Its resolution is so sharp it could read a newspaper on the moon from Earth. This global network was listening when the repeater, FRB 121102, fired again. For that millisecond, the synchronized dishes caught the burst. The data from each location was slightly different, a tiny delay based on its position on the globe. And by calculating those differences, the network could triangulate the signal's origin with breathtaking accuracy. They didn't just place it in its dwarf galaxy. They pinpointed it to a specific tiny region within that galaxy, a cosmic neighborhood. That precise address changed everything. It moved the mystery from a simple what to a detailed where. And the where told a story. The burst wasn't coming from just anywhere. It originated from an incredibly energetic, persistent source of radio waves. A place astronomers already knew about, a place where conditions were anything but normal. This was the first real environmental clue. It was like finding a mysterious, powerful artifact. Before, you could only wonder what it was. Now you could see it was buried in the sacred ground of an ancient temple. The context itself became evidence. The hunt was no longer a search for a needle in a galactic haystack. Scientists now had the haystack, the specific bale of hay, even the strand of hay the needle was stuck in. The question became, what kind of cosmic forge exists in such a place, and what could possibly survive at its heart? The needle had a name. It was April of 2020. A burst erupted, but not from some distant galaxy. It came from our own cosmic backyard, the Milky Way. Two instruments caught it almost at the same time. The CHIME telescope in Canada and a smaller array in the US called STARE-2. This burst, FRB 2020-0428, was 1,000,000 times closer than any we'd seen before. And for the first time, astronomers didn't have to search. They already knew where to look. The burst came from a known object, a star with a designation like a license plate, SGR 1935+2154. That was a magnetar, a specific type of neutron star. To get the significance, picture a star more massive than our Sun. When that kind of star dies, it explodes. A supernova, what's left collapses under its own gravity. It becomes so dense, a teaspoon of it would weigh as much as a mountain. That's a neutron star. Now take that and give it a magnetic field, 1,000 trillion times stronger than Earth's. That is a magnetar, by definition, one of the most extreme environments in the universe. And this particular magnetar was already known to be active. It was emitting X-rays and gamma rays, a sign it was undergoing what astronomers call a starquake. Think of it as a seismic event, but on a stellar scale. The crust of this dense, magnetized object was cracking, shifting under unimaginable strain. And during that violent episode, it released the radio burst the telescopes detected. The energy matched the profile, the distant, extragalactic fast radio bursts. It was the same phenomenon, just happening right next door. This was the pivotal moment. The field had been waiting for it. It gave the first tangible evidence, a smoking gun for at least one source of these signals. Not all FRBs might come from magnetars. But this proved these exotic stellar corpses could produce them. The connection made sense. A magnetar's immense magnetic field acts like a cosmic battery. It stores staggering energy. A starquake could suddenly release that pent-up power, twisting magnetic field lines, accelerating particles, to create a brilliant, fleeting flash of radio waves. A fast radio burst. For astronomers, it was like finally seeing the engine of a mysterious vehicle. They'd only ever seen the headlights streaking across a distant highway. Now they had a blueprint. They could study the mechanics up close, watch the before, during, and after. The distant, repeating bursts from other galaxies could now be modeled against this local example. The mystery wasn't solved, but it had been cornered. We'd identified one of the universe's most powerful voices, and it belonged to the ghost of a star shaking itself apart. A magnetar is a star turned inside out. Its power doesn't come from nuclear fusion like our sun. It comes from gravity, from a magnetic field. To understand how it can shout across the universe, you look at how it's born. It starts with a star much larger than our own. When that star runs out of fuel, its core collapses. There's a supernova. What's left is a neutron star. That's the entire mass of our sun, compressed into a sphere the size of a city. A sugar cube of that material would weigh as much as a mountain. That's the dense heart of it. But a magnetar pushes that further. During that violent birth, if the star is spinning fast enough, its internal dynamo amplifies the magnetic field to almost unimaginable levels, a field 1,000 trillion times stronger than Earth's. This isn't just a strong magnet, it's a fundamental force. It reshapes the fabric of space around it. At that intensity, the magnetic field becomes a tangible, straining presence. It grips the star's solid crust. It twists it. That creates immense stress. Like winding up a spring made of material stronger than steel. Eventually, something has to give. The crust cracks. Astronomers call it a starquake, but it's nothing like tremors here. This is a rupture on a stellar scale. The entire surface of that city-sized star shifts in an instant. The pent-up energy in those twisted magnetic field lines is released. In a catastrophic snap, it accelerates a storm of particles to nearly the speed of light, and in that chaotic event, the star unleashes a flash across the electromagnetic spectrum. From gamma rays down to radio waves, that flash in the radio part of the spectrum, lasting just milliseconds, is what we detected from our galactic neighbor. It was the signature of a magnetar's agony, a direct observation that these cosmic powerhouses can produce the precise kind of signal we've been chasing from distant galaxies. This established them not just as a theoretical possibility, but as a proven physical engine, one capable of concentrating the energy of a star's lifetime into a blink. But confirming one source doesn't mean the puzzle is complete. It just gives us a key, a way to start deciphering all the other, stranger messages still echoing from the dark. A single key doesn't open every door. Magnetars gave us a clear answer for one kind of burst, but the cosmos isn't usually that simple. The more we listen, the more varied the signals get. Some sources, like that first repeater, fire off dozens of bursts in a chaotic pattern. Others have only ever spoken once. This diversity in behavior suggests a diversity in origin. We might not be hunting one cosmic creature, but an entire zoo. The one-off bursts, the single flashes, they point to events where something is destroyed. The leading idea there involves collisions. Two of the densest objects in the universe, neutron stars, spiraling inward over millennia until they finally merge in a final crash. That collision would release a titanic burst of energy, a one-time scream, or a white dwarf star torn apart by a black hole. These are final acts they can't repeat. But then there are the repeaters, the sources that survive. For those, astronomers look to systems that can endure. A highly magnetized neutron star interacting with a disk of debris, maybe the remains of a shattered asteroid belt. Material falls onto the star's surface, triggering explosive flashes without destroying the engine, or a special type of supernova that leaves behind a highly active remnant. Each model tries to explain the resilience, the ability to fire again. Then there are the ideas that push at the edges, cosmic strings, these hypothetical defects in spacetime, snapping and releasing energy. Or more speculatively, the possibility of advanced technology, a civilization using a powerful beam for propulsion, sweeping past our line of sight. Most scientists consider that extremely unlikely, but the fact it's even discussed shows how strange these signals are. They force us to question everything. This proliferation of theories isn't confusion. It's a field alive with possibility. Every new burst, every new piece of data is a test. It rules some ideas out and gives others more weight. The debate drives the science forward. We're in the middle of a detective story, with the universe providing clues that are tantalizing and frustratingly brief. Each millisecond flash is a piece of evidence, and we're still assembling the picture. The problem was perspective. Astronomers had been looking through a keyhole. They were only seeing the brightest flashes. To really understand fast radio bursts, they needed to see the whole sky. They needed a new kind of eye. That eye is CHIME, the Canadian Hydrogen Intensity Mapping Experiment. It doesn't look like a telescope, no giant dish. It's a stationary array, 4 half-cylinder reflectors, each about the size of a football field. They're lined up in a row in British Columbia. It was built to map the faint radio glow of hydrogen, to study the expansion of space, but its design was perfect for another hunt. CHIME doesn't point, it stares. Its wide, fixed view scans the entire northern sky every day as the Earth rotates. It's like a security camera on the cosmos, recording everything that flashes. When it came online, it didn't just find a few new bursts, it opened a fire hose. CHIME began detecting bursts by the dozens. Then by the hundreds, almost overnight, the field changed. Astronomers went from analyzing a handful of rare events to managing a flood. They were no longer just detectives on a single case. They became demographers, studying an entire population. That was the revolution. With so many signals, patterns emerged, patterns that were invisible before. They found repeaters weren't a one-off, they were a common class. Some sources were hyperactive, firing off bursts in frantic clusters. Others were quiet for months. Then they'd suddenly wake up. CHIME Constant Watch caught these changing behaviors. It could see the life cycles of these distant engines in real time. The volume of data allowed for categorization. Not all bursts are the same. Some have simple, clean profiles. Others are more complex. They have substructure, hinting at intricate processes within that millisecond. By sorting them, astronomers could ask new questions. Do the one-off bursts and the repeaters come from different galaxies? Are they in different cosmic environments? This statistical approach is turning mystery into science. We're beginning to map their true distribution, to understand not just what they are, but how common they are. And every new burst CHIME finds is another data point, another clue in the puzzle of what fills the dark between the stars. A burst is a messenger. It carries a story, but the story isn't just in its power. It's in the fabric of the signal itself. Beyond just arriving, a fast radio burst has a kind of fingerprint. And that fingerprint is encoded in its polarization. Think of light or radio waves like a rope. If you shake one end up and down, you get a wave that vibrates in one plane. That's polarized. If you shake it in all directions, that's unpolarized. Now, many signals from space start out polarized. They have a specific orientation when they leave their source. And that's a crucial detail because that orientation can change on the journey. the burst travels across the cosmos, and it's not moving through a perfect vacuum. It's passing through clouds of magnetized gas, a thin plasma threaded with magnetic fields, and when a polarized wave moves through an environment like that, something happens. The plane of its polarization rotates, it twists. That effect is called Faraday rotation. The amount of twist depends on two things: the strength of the magnetic field it's passing through and the density of the electrons in that plasma. And it's a cumulative effect. Every cloud, every filament the signal grazes adds a little more twist to the message. So when astronomers catch one of these bursts, they don't just measure its arrival or its brightness. They analyze its polarization with extreme precision. They measure that final, twisted angle, and by doing that, they can work backwards. They can calculate the total magnetic influence the signal experienced. Across a billion light-year journey, this is revolutionary. For the first time, we have a tool to map the magnetic fields in the vast, empty spaces between galaxies. Places so diffuse we could never study them directly. It's like being in a dark forest at night. Someone far away flashes a beacon, you see the light. But if that light passed through a series of frosted, twisted windows on its way to you, the beam would be changed. By studying the pattern in the light that reaches you, you could learn something about those unseen windows. Their thickness, their quality, their twist. Fast radio bursts are those beacons. The space between galaxies is those windows, and the Faraday rotation is the telltale twist in the light. This turns every burst from a mystery into a probe. Each one is a fleeting, brilliant survey, a survey of the universe's most invisible architecture. They're helping us chart the magnetic skeleton of the cosmos itself, a structure we knew must exist but could never touch before. The bursts aren't just cosmic anomalies anymore. They are becoming guides to the dark. That journey has its own hidden ledger. Every electron the signal passes through leaves a mark. That dispersion, the stretch in the burst's arrival time, it's more than a distance marker. It's a cosmic census. Each burst traveling a billion light years is counting. It's tallying every free electron along its path, and that becomes one of their most powerful features. Because most ordinary matter in the universe, the atoms in stars, planets, us, it isn't in those bright objects, it's out in the dark. It's a diffuse, superheated gas. A thin soup of protons and electrons, spread so thinly between galaxies it's nearly invisible. Astronomers have had this problem for decades. They'd add up all the normal matter they could see in galaxies and clusters, and it only came to about half of what the Big Bang's recipe said should be there. The rest was missing, not dark matter, that's something else. This was regular atoms just hiding in plain sight in the vast intergalactic voids. A fast radio burst is the perfect tool to find them. As it travels, it interacts with every one of those free electrons. The more electrons it passes, the more its signal gets delayed and stretched. So by measuring that dispersion carefully, astronomers get a total. The total number of electrons along that precise line of sight. And if they know the distance to the host galaxy, which they often do now, they can do a simple division. Take the total count and divide it by the journey's length. The result is an average density, the density of that invisible intergalactic gas. It's like trying to measure humidity in the air across a continent. You can't put sensors everywhere, but if you could fire a laser from one coast to the other, measure precisely how much the light scatters, you could calculate the average moisture content along that entire path. FRBs are those lasers, and the universe is the continent. By using bursts from many different distances and directions, scientists are starting to build a three-dimensional map. A map of where the missing matter is. Early results are confirming the theories that half of the universe's ordinary atoms are indeed floating in these immense, dark reservoirs. The bursts are acting as scales, weighing the cosmos in a way we never could before. They started as a mystery, became a Magnetar's signature, and now they're evolving into something even more profound. A fundamental instrument for taking the universe's inventory. Pinpointing a location does more than find a source. It finds a home, and the homes for these repeating bursts, they aren't quiet. They're cosmic war zones. When they traced the repeater FRB 121102 to its dwarf galaxy, they didn't just find a dot, they found a specific neighborhood inside it. A place with immense, persistent radio emission. It wasn't a calm void, it was a maelstrom, something like a violent star-forming nebula, or maybe the chaos near a massive black hole. The signal came from a place of raw energy that added a piece of context. It suggested the ability to repeat, to survive those blasts might not just be about the object. It could be about the environment that fuels it. Think of a powerful engine. Put it in a quiet garage, it runs out of fuel and stops. But put it in the middle of a raging river with a current turning its turbines, it could run forever. The chaotic, magnetized environment around a repeater could be that river, a persistent source of material or energy keeping the engine firing. One idea is a magnetar in a tight orbit around a black hole. The black hole's gravity could strip material from the star, feed it onto the magnetar, trigger repeated outbursts. Or the magnetar could be embedded deep in a dense nebula, the swirling remains of the star that birthed it, constantly interacting with that chaotic cloud. So repeaters become a distinct class. They're not just objects, they're systems, an object plus its environment. The one-off bursts might be the final death screams of isolated objects. But the repeaters, they could be the chronic, booming voices of engines trapped in a cosmic forge. Their persistence is a clue. It says they're being fed, stressed, energized by something larger than themselves. Their location isn't just an address, it's a diagnosis. It points to the conditions required to create a signal that refuses to stay silent. And with every new repeater we locate, we examine another kind of extreme neighborhood. Building a catalog of the universe's most volatile places just by listening to the voices shouting from inside them. The repeaters are rare. Most sources, they flash once and then go silent forever. These are the one-off bursts, a single flash and then nothing. That silence is a kind of signature. It means the event was final. The engine didn't just stutter, it was destroyed. The likely causes are among the most violent things we know. One is two neutron stars merging. You have these remnants of dead stars, each the size of a city but incredibly dense, orbiting each other. They spiral in for ages and then they collide. That collision is catastrophic. It sends ripples through space-time gravitational waves, and in that final moment, it can also release a huge burst of radio waves. A one-off FRB. After that, the source is gone. It becomes a black hole or maybe a hypermassive neutron star that collapses immediately. Another possibility is a single neutron star collapsing under its own weight. Even they have a limit. If one pulls in too much material from a companion star, or if it's just born too heavy, it can reach a tipping point. Gravity wins. It implodes in an instant, becoming a black hole. That sudden, total transformation could also power a final radio shout. These ideas fit, but they create a problem. If the source destroys itself, you only see it once. There's no return address. Pinpointing its exact origin in a distant galaxy becomes incredibly hard after the flash fades. It's like trying to find the exact spot of a lightning strike in a distant forest long after the storm. You know it happened, but the evidence is gone. That makes the one-offs fundamentally harder to study than the repeaters. We have far less data. We don't know their environments as well, or their host galaxies, their precise locations. Are they born in the same chaotic places as repeaters, or in quieter, more isolated parts of galaxies? We don't know, and that leads to the central question. Are one-offs and repeaters two completely different families, or are they different chapters in the same story? Could a repeater, after centuries of activity, eventually have a final, catastrophic outburst and become a one-off? Or are the engines that repeat just built differently, able to survive their own fury? The silence after a one-off burst is part of its message. It's the sound of a door closing. And we're left to wonder what was on the other side. The bursts were always about frequencies. For years, astronomers listened in a certain range, around 1 to 2 gigahertz. It's a clear part of the radio spectrum. That's where they found the first fast radio bursts. But if you only listen on one channel, you're only getting part of the story. So they wondered if these things were also broadcasting lower down, much lower, into the megahertz range below 400, and they found them, low-frequency bursts. But detecting them is harder. The universe is noisier down there, more interference from Earth and from space. The signal has to fight through it, and then there's the journey itself. Lower frequency waves are more vulnerable. They travel through this thin plasma that's everywhere, between stars, between galaxies. It's like shouting into a fog. Your voice gets scattered, it smears. That's what happens to the burst. The electrons in the plasma scatter the waves. A millisecond flash gets stretched. It becomes a longer, distorted echo. Sometimes it gets smeared out completely, lost before it gets here. But that distortion, that scattering, it's not just noise. It's information. If you see the same burst at a high frequency and a low frequency, you can measure the scattering, exactly how much it got smeared. And that tells you about the material it passed through, the density, the turbulence. Was it a smooth trip through quiet gas, or did it go through something violent right near the source? The amount of smearing has the answer. Each low-frequency burst is like a new light turning on. It shows you the details of the landscape. So now, by listening across the whole spectrum, from the high notes to the low rumbles, you're not just hearing the shout. You're hearing the echo of that shout, how it bounced off every wall, every corridor in this immense hall. It adds a dimension to the map. It helps us understand not just where the bursts come from, but the nature of the space they had to cross to get here. That millisecond flash is just one part of the story. It's a message on one channel, but the same event could be shouting on every channel at once. Astronomers aren't just listening for these bursts. They're watching for them. They've turned the whole sky into a net, waiting to catch any other signal that arrives at exactly the same moment. This is the hunt for counterparts. A search across the entire spectrum of light, from the highest energy gamma rays down to the visible light we see. The idea is powerful. If a fast radio burst also produces a flash of X-rays or a flicker of optical light, that tells us so much more about the engine that created it. Each type of light comes from a different physical process. Seeing them together is like getting a full medical scan instead of just listening to a heartbeat. You see the structure, the cause, the aftermath. We already have one perfect example, the galactic burst from our own Magnetar. That event wasn't just a radio spike. Space telescopes saw it light up in X-rays at the very same instant. That simultaneous detection was the final proof linking Magnetar starquakes to at least some fast radio bursts. It showed the event was a full-body eruption, not just a radio whisper. For the bursts from other galaxies, the cosmological ones, catching a counterpart would be a monumental breakthrough. Imagine pinpointing a burst, and within that same millisecond, a space telescope detects a brilliant gamma-ray flash from the same spot. That would immediately rule out dozens of theories. It would point squarely to one. It would reveal the physical process at work as clearly as if we were there. This quest defines the cutting edge of time-domain astronomy. It's a global, coordinated race against the clock. When a radio telescope like CHIME detects a burst, it sends out an alert within seconds. That alert flashes to observatories around the world and in space. Gamma-ray satellites like SWIFT or Fermi swing to look. Optical telescopes in Chile or Hawaii point their lenses. They're all trying to capture that first glow, the fading afterglow. anything that might linger for seconds or minutes after the main event. It's a frantic, international effort to catch a ghost, and so far, for the distant bursts, the counterparts have remained elusive. That silence is itself a profound clue. It tells us that whatever is happening in those faraway galaxies, it might be different from our local magnetar, or perhaps the light is there, but it's too faint, or it fades too quickly for our current tools to see. Every non-detection narrows the possibilities. This multi-messenger hunt transforms the mystery. It's not just a listening exercise anymore, it's a full-scale surveillance operation. We are waiting for the universe to make a mistake, to reveal itself not with one signal but with two, and when it does, that single moment will illuminate the darkness like nothing before. The search itself has gotten huge. That's the challenge now. You have thousands of bursts. Each one is just a little packet of data, but it holds a dozen different measurements. So it becomes this ocean of information. To handle that flood, you need more than telescopes. You need librarians. You need these sophisticated databases and catalogs. That's the new backbone of the field. Projects like the Fast Radio Burst Catalog, they're the central archives. Every flash that gets detected is logged there. Its properties are recorded, the dispersion measure, its width, its brightness, the polarization. It's not just a list, it's a living map of the whole phenomenon. And by organizing the data that way, scientists can run queries. They can ask questions across the entire population. Do all the repeating bursts have higher magnetic measures? Do the one-off bursts come from older galaxies? These catalogs turn a collection of mysteries into a statistical dataset. The patterns that answer the big questions, they won't come from one brilliant flash. They'll come from the subtle trends, the ones hidden across thousands of them. And this volume of data, it opens the door to a new kind of explorer, the citizen scientist. Initiatives like Breakthrough Listen, they use some of the world's most sensitive radio telescopes to search for technosignatures, but they also analyze fast radio burst data. They have sophisticated algorithms scanning for patterns, but sometimes the human eye and brain can spot an anomaly a computer might miss, so projects can invite the public to help. To sift through signal plots, to look for the subtle thing, the strange thing, the outlier. It's a collaborative approach. It leverages a global network of curiosity. It acknowledges that the next breakthrough might not come from a single researcher in an observatory. It might come from a teacher, or an engineer, or a student looking at data on their home computer. The puzzle of fast radio bursts has grown. It's beyond astrophysics now. It's also a frontier in data science, a test of our ability to find meaning in the cosmic noise. And in that effort, every curious mind becomes a potential partner. A catalog is only as good as the telescope behind it, and these signals are so fast, so faint, they need a new kind of instrument. One that doesn't look at a single star, but watches the whole sky at once, with enough sensitivity to hear a whisper from the very edge of everything we can see. That need has started a kind of arms race, a global push to build the ultimate listener. So the next generation of observatories, they're being engineered from the ground up for this. In California's high desert, the Deep Synoptic Array is coming online. It's not one big dish. It's 110 individual radio antennas packed tight into a field. Together they create one powerful eye with an enormous field of view. That design is the revolution. It lets the array stare at a huge piece of sky, night after night, with incredible sensitivity. Built to catch not just the loud bursts but the faint, distant ones we've been missing. It could find hundreds every year, and that's just the start. The real game changer is still coming, the Square Kilometer Array. This isn't just a new telescope, it's a continent-spanning project. Thousands of antennas spread across remote sites in South Africa and Western Australia. When it's finished, its total collecting area will be about 1 square kilometer. That gives it a raw sensitivity that dwarfs anything we have, so sensitive it could detect an airport radar on a planet tens of light years away. For fast radio bursts, that means something. The square-kilometer array won't just find the bright, easy signals. It will hear the murmurs, the faint population that's invisible now. It will detect them by the thousands, maybe tens of thousands. We'll move from studying rare events to mapping a common phenomenon. This coming flood of data will change the field completely, shifting the focus from solving individual mysteries to a mature, statistical science of the transient sky. Instead of asking what made that one burst, we'll ask what the distribution of 10,000 bursts tells us. About the history of galaxies, the structure of the cosmic web, the life cycles of the most extreme objects out there, the telescope stops being just a detector. It becomes a census taker for the cosmos. That brief, brilliant pulse feels unnatural to our human senses. It looks like a signal that was designed. When they first found fast radio bursts, one question was inevitable. Could this be a message? And that idea wasn't dismissed out of hand. The signals had these characteristics that seemed almost engineered. They were extremely bright, very short, coming from a great distance. They fit a profile of what a deliberate, powerful beacon might look like. For a while, the possibility that these were technosignatures, evidence of advanced intelligence, was a serious part of the conversation. A hypothesis to be tested like any other, and that speculation, while captivating, it served a purpose. It forced a rigorous examination. Scientists had to ask what exactly would make a signal look artificial. How do you tell the difference between a cosmic accident and a cosmic hello? The intense study of fast radio bursts gave the answers. As the natural origins, like magnetars, became clear, they gave us a catalogue of what nature can do on its own. The universe is perfectly capable of creating these fleeting, incredibly powerful radio flashes without any help. And that knowledge is a gift to the search for extraterrestrial intelligence, to SETI. It acts as a filter. By understanding the full range of natural astrophysical phenomena, SETI researchers can refine their search. They can look for signals that break the natural mold. A signal that repeats with a precise mathematical pattern, like a sequence of prime numbers, or a transmission confined to an impossibly narrow band of frequency, something no known cosmic process can produce. Fast radio bursts, in their wild variety, have helped define the baseline of cosmic noise. They've shown us what not to get excited about, so we can save our wonder for the signal that truly doesn't fit. And the tools developed in the hunt for these bursts have become SETI tools. The same software pipelines that sift through terabytes of telescope data to find a millisecond spike are perfect for searching for an intentional beacon. The methods for pinpointing a burst's origin across billions of light years are the very methods needed to locate a potential source of a message. So the puzzle of fast radio bursts has inadvertently trained an entire generation of instruments and algorithms to be better listeners. Not just to the universe's violence, but to its potential whispers of companionship. So while the bursts themselves are almost certainly natural, their legacy intertwines with the greatest question. They've sharpened our search. They've shown us the cosmos is stranger and more creative than we imagined, capable of mimicking the very signals we once thought only intelligence could make. And that sets a higher bar, a more exciting one. It means if we ever do hear a signal that passes this new test, that stands out from the natural fireworks, we might finally have something truly extraordinary to consider. The real value of these signals might not be in the signals themselves. It's in what they can show us. They're like lighthouses, shining through the most extreme places in the universe. And that trip makes them perfect for testing the laws of physics. When a signal travels for billions of years, it's not just moving through empty space. It's moving through gravitational fields, through clouds of exotic particles, through the fabric of space-time. every single interaction, even a tiny one, could leave a mark on the signal. A fingerprint of the universe's secrets. There's one profound test. It involves Einstein's principle of equivalence. That's a cornerstone of his theory of general relativity. It says simply that all objects fall at the same rate in a gravitational field. It doesn't matter what their mass is or what they're made of. A feather and a hammer in a vacuum hit the ground at the same time. This principle also means all forms of energy, including light, should be affected by gravity in the same way. But some theories of quantum gravity suggest that at the most fundamental level, this might not be perfectly true. Not for all energies. They predict that extremely high-energy photons, the particles of light, might interact with gravity just a little bit differently than lower-energy ones. This is where a fast radio burst becomes a laboratory. Its flash isn't one single color. It's a broad spectrum of radio photons from high energy to low, all emitted at the exact same instant from the same place. According to Einstein, they should all travel along identical paths through the curved spacetime of the universe. They should arrive at our telescopes together. But if quantum gravity effects are real, the highest energy photons in that burst might take a very slightly different path. They could arrive a fraction of a second earlier or later compared to their lower energy siblings. The difference would be unimaginably small. Maybe just a few millionths of a second over a journey of 1 billion light years. But with precise enough measurements of these bright, clean signals, we might be able to detect it. It would be a crack in our understanding of gravity. A whisper of a deeper theory. Beyond gravity, these bursts could probe the invisible architecture of the cosmos in other ways. As their signals pass through vast halos of dark matter surrounding galaxies, could the mysterious particles interact with the radio waves in a detectable way? Could the signal's polarization twist in a pattern that reveals the nature of dark energy, the force that's accelerating the universe's expansion? Each burst is a controlled experiment we could never run on Earth. It uses the universe itself as the apparatus. With distances and energies we can't possibly replicate, we're learning to read the fine print written into these cosmic telegrams. Searching for deviations from the known laws, deviations that would point to something entirely new. The puzzle of what makes them is now a gateway to an even grander quest, understanding the rules that govern everything. That one blip in the data, its ripples went way past the observatory. There's a hidden power in a cosmic mystery. Fast radio bursts, the pursuit of them, it's become an engine. For innovation, to catch a millisecond signal, you need new computers, new algorithms to sort through a tidal wave of data in real time. And that software, that hardware developed for this hunt, it's finding uses elsewhere now. In medical imaging, in telecommunications, it's the classic basic research story. You chase a question just to know, and along the way you invent tools. Tools you never knew you needed, tools that change how we see things. This quest, it's also redrawn the map of collaboration. It's global. A burst picked up by a telescope in Canada sends alerts to instruments in Chile, South Africa, Australia, orbiting satellites, teams from dozens of countries. They share the data, they compare notes, they build those vast public catalogs together. In an age of division, that silent flash from a distant galaxy, it pulls humanity into a shared project of understanding. It reminds you, the night sky is a common heritage. Its puzzles, they belong to everyone, and that shared curiosity, it has a heartbeat, a cultural one. The story of these bursts, it has all the pieces. Of great drama, a mysterious signal, years of doubt, dead ends, that startling discovery in a microwave oven, then the triumphant pinpointing of a source. No wonder it captures the imagination. It's in documentaries, best-selling books. It inspires episodes of science fiction, where writers play with that tantalizing what if. What if it's intelligent? News about a new, strange burst, it still grabs headlines. It invites everyone to wonder for a moment what's really out there. And that engagement, it's not a side effect, it's a vital outcome. Every child who hears this and looks up at the stars with a new question, that's a potential future scientist. Every citizen who feels a thrill at the word Magnetar or the cosmic web, they become a stakeholder in our collective exploration. The mystery makes the universe feel personal, alive with possibility. In the end, that might be the most lasting legacy of these fleeting flashes. They show that the most profound questions, the ones that seem purely abstract with no obvious use, those are the ones that drive us forward. They force us to build better instruments, to forge new partnerships, to explain the incredible to our neighbors. The search for the source of a fast radio burst, it is itself a source. A source of technology, of cooperation, and of wonder. It proves that looking deep into the dark, it's not an escape from our world. It's a fundamental way to understand our place within it. And to inspire the ones who will look even deeper one day. A fast radio burst is a brilliant flash. It demands the fastest reflexes. To capture one is like catching a shooting star. But the real prize isn't the flash itself. It's what comes after, the afterglow, the fading light in X-rays or in optical wavelengths. Those secondary signals hold the keys to the engine. And they vanish in moments, sometimes seconds, sometimes minutes. So the entire process from detection to alert has to happen at the speed of thought. This is real-time astronomy, a global race conducted by machines. When the radio wave from a burst finally washes over a telescope dish after traveling for 1 billion years, the clock starts. That raw data is a torrent, noise and static. Buried in that river is a single spike. It lasts 5 milliseconds. Finding it manually would be impossible. So sophisticated software pipelines take over. Complex algorithms running on supercomputers, often right at the observatory. They ingest the data stream in real time, sifting through the cosmic static, looking for the fingerprint, the short duration, the specific dispersion. Within seconds of the signal hitting the telescope, these pipelines can identify a strong candidate. They make a split-second decision. Is this real? If the answer is yes, an automated alert blinks into existence. It's not an email. It's a formatted digital telegram broadcast across global networks. The astronomer's telegram, the gamma-ray coordinates network. The alert contains the burst's coordinates, its estimated distance, its brightness, and it goes out to a pre-subscribed list of partners. Space telescopes in orbit, like Swift or Fermi, receive the ping. They can immediately slew to point their instruments at that patch of sky. Ground-based optical telescopes in Chile or Hawaii get the coordinates. They can interrupt their planned observations to swing toward the source. This entire chain, from detection to worldwide alert, can happen in under 10 seconds. The goal is to catch the echo of the explosion. Imagine a thunderclap. The burst is the initial, deafening crack. The multi-wavelength afterglow is the long, rumbling thunder that follows. Reverberating through different materials, by capturing that secondary rumble in X-ray or visible light, scientists can learn about the environment. Was it surrounded by dense gas? Did it leave a hot, expanding remnant? Each color of light tells a different part of the story. Without this rapid response network, that story is lost forever, fading into the background noise of the universe as quickly as it appeared. This system transforms a solitary, mysterious blip into a rich, multi-faceted event. It turns a single witness into an entire jury of instruments, each examining the evidence from a different angle. The challenge is immense, a constant push against the limits of computing speed and network latency. But every time it works, when a space telescope confirms a faint X-ray glow from the exact same spot, the fleeting mystery becomes a little more permanent. A little more understood, it's a testament to human ingenuity, building a nervous system for the planet just to listen for the universe's shortest stories. Statistics have turned whispers into a chorus, with thousands of bursts catalogued now from surveys like CHIME. The mystery has shifted. It's not about solving a single puzzle anymore. It's about understanding an entire population, how these flashes are scattered across the cosmos, whether they're even or if they cluster in certain regions. And the answer is starting to take shape. It paints a picture of a universe far more dynamic than we thought. Early analysis of this flood of data shows something profound. Fast radio bursts aren't rare, exotic accidents. They're common, astonishingly common. Current estimates say across the entire observable sky, thousands of these events likely happen every single day. Think about that. A cosmic phenomenon we only discovered 15 years ago is actually happening all the time, all around us. We were just listening with the wrong ears. Or looking at too small a piece of the sky. That sheer rate is the first major statistical revelation. It tells us these bursts are a standard feature. A normal part of the universe's activity, not a fluke. But the statistics go deeper than just a count. By studying the distribution of their brightness, how many are incredibly luminous versus how many are faint, astronomers can start to model the population of their sources. It's like understanding a forest, not just by counting the trees, but by measuring their heights. If you only see the tallest giants, you might think the forest is sparse. Just ancient redwoods, but if you have a tool that can also see the saplings, the medium-sized trees, you get the true picture, a thriving, diverse ecosystem. The distance measurements add another layer. The redshifts, they tell us when in cosmic history these bursts are happening, whether they're only in young, early galaxies or if they occur in older, more settled ones too. The data so far suggests a broad range. Fast radio bursts have been detected from galaxies both near and far, from different cosmic epochs, which means the engines that produce them have been active for billions of years. They're not a recent development, they're a persistent thread woven through its history. This statistical approach moves the question from what made that one burst to what does the existence of this entire population tell us about the universe. It constrains our theories. If a proposed source is too rare or too short-lived to account for the thousands of daily events we infer, then it's likely not the whole story. The statistics force the models to evolve, to account for abundance and for longevity. In the end, this transforms fast radio bursts from celestial anomalies into fundamental probes. Their distribution across the sky and through time is a new kind of map. A map not of stars or galaxies, but of the most violent, energetic, fleeting moments in the cosmos. Reading this map means we're no longer just studying strange signals, we're taking a census of the universe's most extreme neighborhoods, learning how common they are, and starting to understand their role in the grand, evolving ecosystem of everything. The galaxy that hosts a burst, that's its biography. For a long time, we only had a few entries in that book. The first repeater we found was in a tiny, turbulent dwarf galaxy, and that fit a neat story. It made sense, extreme objects born in extreme, primitive places. But then we pinpointed more bursts, and that simple story just shattered. Now we're walking through a host galaxy zoo. The variety is breathtaking. Some bursts come from galaxies just like our Milky Way. Grand spirals, metal-rich as astronomers say, these are mature, settled neighborhoods, not the chaotic nurseries we first imagined. Then other signals come from the opposite end of the spectrum. Those faint, dim dwarf galaxies, where star formation is a frantic, all-consuming fire, and there are bursts from galaxies that are neither elliptical blobs or interacting galaxies twisted by gravitational dances with their neighbors. This diversity is a fundamental clue. It complicates the search for a single, universal progenitor. It tells us the recipe for a fast radio burst isn't exclusive to one type of cosmic kitchen. The conditions to create that millisecond scream can arise in many different galactic environments. A massive metal-rich spiral and a tiny primordial dwarf, they seem to have almost nothing in common, yet both have produced these incredible signals. So what does that mean for the engines themselves? It suggests the mechanism might be versatile. Maybe it's tied to a phase in a star's life cycle, rather than to a specific, rare type of galaxy. Different paths could lead to the same brilliant endpoint. In a dwarf galaxy, a star might be born with the perfect, violent conditions to become a highly magnetized neutron star right from the outset. In a massive spiral, an older neutron star might be rejuvenated by a catastrophic event, pulling material from a companion star or colliding with another dense object, triggering a final, furious outburst. This host galaxy zoo does more than catalog addresses. It links the burst mechanism to the grand narrative of galactic evolution and stellar death. By studying the demographics, which types of galaxies produce which kinds of bursts, repeaters versus one-offs, we can trace the life story of the most extreme objects in the universe. We start to see them not as isolated freaks of nature, but as natural outcomes, woven into the fabric of how galaxies live and change and even die. Each localized burst adds a new specimen to this zoo, helping us understand the full ecosystem of cosmic violence. A theory is a story. It's a possible explanation for what we see. But with fast radio bursts, the stories are about environments that are so extreme they defy simple intuition. Gravity is crushing. Magnetic fields are strong enough to shred atoms. And the question is, how do you test an idea about a place like that? You can't build it in a lab, so you build it in silicon. Theorists build entire cosmic engines inside supercomputers. These aren't simple animations, they're intricate mathematical worlds, governed by the full set of laws we know, the equations of magnetohydrodynamics, general relativity, plasma physics. In these virtual labs, scientists can create a magnetar. They can wind up its magnetic field to the breaking point, and then they can watch, in exquisite simulated detail, what happens when it snaps. The goal is precise, to see if this digital starquake can produce not just a flash, but the right kind of flash, one that matches the real signals from deep space. Does the simulated burst last the correct fraction of a second? Does it shine with that impossible radio brightness we observe? And most tellingly, does the light carry the specific, twisted signature of polarization that our telescopes actually measure? Each one of these characteristics is a constraint. It's a filter, a simulation that produces a flash, but the wrong kind of flash is a story that doesn't fit the facts. It gets discarded. The process is a constant conversation between the virtual and the real. An observation from a telescope provides a new detail, maybe a burst with an unusual double peak. The modelers go back to their code. They ask, what tweak to our simulated engine could create that? Maybe it requires a specific arrangement of magnetic field lines, or a particular density of plasma around the star. They run the simulation again. They see if the new virtual output now matches the new real-world data. This feedback loop is how understanding is forged. It turns speculation into rigorous, testable physics. One leading simulation might focus on a magnetar's flaring magnetosphere, modeling how a sudden reconnection of magnetic field lines can blast a storm of particles outward. Another might simulate the chaotic jet from a collapsing massive star, seeing if the interaction of that jet with surrounding material can generate a coherent radio scream. Yet another might recreate the final milliseconds of two neutron stars merging, tracking whether the turbulent aftermath could produce that brief, brilliant radio pulse we detect as a one-off burst. Each simulation is a hypothesis made tangible. When it succeeds, it does more than explain a signal. It reveals the invisible choreography of forces at work. It shows the sequence of events inside that millisecond. The initial crack, the avalanche of particles, the shaping of the radio wave as it fights its way out of a maelstrom of magnetism and plasma. The simulation becomes a window, a way to witness in slow motion a catastrophe that happens too fast for any instrument to truly capture. This is the work of turning a cosmic mystery into a known phenomenon. Not by looking harder, but by thinking deeper, by building the universe inside a machine to learn how it builds its most fleeting wonders. The search for fast radio bursts is a global effort. It started with one telescope, the Parkes telescope in Australia. That's where the first one was found, just sitting in old data. That discovery set everything in motion. Now you have other instruments. CHIME in Canada, with its stationary cylinders, scans the sky every day. There's a network in Europe, dishes linked together to act like one huge telescope. There are instruments in China, in India, in the mountains of Chile. When a burst happens, it's often seen by more than one of these. An alert goes out across a network in seconds. Data comes in from telescopes on opposite sides of the planet, and it's all combined and analyzed. This isn't just sharing information. It's building one single sensor, a planet-sized sensor. A nervous system for Earth, listening for the shortest whispers from the universe. The collaboration never stops. When it's night in Canada, the day is starting in Australia. When Europe is asleep, telescopes in Asia are watching. That constant watch is the only way. These events are completely unpredictable. You have to be looking at the right spot in the sky at the exact right millisecond. By having eyes everywhere, we get more chances, but it goes deeper than the hardware. It's a pooling of curiosity. A theorist in Japan works with the latest data from South Africa. Engineers in the Netherlands write software used by observers in California. Graduate students from a dozen countries meet at the same conferences, talking about a new, strange signal. The open sharing of data through public catalogs and fast alerts, that's what keeps the field alive. It means a discovery from one team can be checked and built upon by another team in just hours. That international spirit changes the whole endeavor. No single country, no single university could do this alone. The puzzle is too big, the signals are too brief. It needs the combined intellect, the shared resources, the collective patience of the whole world. In that way, this quest to understand these flashes, it shows something basic about science. It's a human enterprise. It's driven by a shared need to know. The questions are written in the stars for everyone, and the work of reading them belongs to everyone too. A mystery like this, it doesn't stay in the observatory. It travels. It gets into classrooms, planetariums. The story of fast radio bursts, it's a perfect teaching tool. It makes the abstract feel immediate. How do you explain the electromagnetic spectrum? You can talk about wavelengths and frequencies, or you can tell them about a flash so powerful it crosses billions of light years. A shout we can only hear with radio ears, that makes the concept real. It gives the invisible a voice. Science centers use these bursts to tackle scale, the hardest idea in astronomy. The distances are so vast they become meaningless numbers, but a fast radio burst makes that journey tangible. You can say the signal left its galaxy when life on Earth was just single-celled organisms. It's been traveling through the dark all this time, and we just caught it. That stretch of time, that immense journey, it becomes a story, one a mind can grasp. But maybe the most valuable lesson isn't about physics or distance. It's about the process of science itself. The narrative of fast radio bursts is a masterclass in the scientific method. It starts with an accidental discovery in old data. Then comes the healthy skepticism, the rigorous doubt, the false leads like the microwave oven puritans. The slow, collaborative work to rule out every ordinary explanation. the breakthrough moment finding the first repeater, and then the ongoing global effort to build better tools to test new theories. This entire arc shows that science isn't a list of facts. It's a living, breathing, sometimes messy detective story. It progresses through curiosity. Through failure, persistence, shared wonder, online platforms, documentaries, they bring this story to millions. They turn complex research into accessible adventures. A child watching a video about magnetars isn't just learning about neutron stars. They're being invited into a grand human endeavor. They see that the biggest questions belong to everyone. That you can start with a mystery whispered from the void and through ingenuity and cooperation begin to find answers. This outreach, it does more than inform. It inspires the next generation of scientists, engineers, curious minds. It reminds all of us that the universe isn't a static backdrop. It's an active, dramatic place, full of puzzles waiting for those who dare to listen. The atmosphere protects us, but it also filters the sky. For radio astronomy, it blocks parts of the spectrum. The low frequencies, the high ones. To hear everything, you have to get above it. The next step with fast radio bursts probably won't be on a mountain. It'll be in space, in that quiet. Think about putting a radio telescope on the far side of the moon. The moon itself becomes a shield. It blocks all the noise from Earth. The cell phones, the satellites, the TV signals, you'd have silence, perfect radio silence. An array there could detect bursts at frequencies we can't see from the ground at all. It could pick up the faintest signals, the long, low rumbles that get smeared out by our ionosphere before they even arrive. We might find a whole new category of bursts. Ones we don't know about yet, and a system in space allows for instant coordination. A satellite dedicated to finding these bursts could see a flash. Then, in milliseconds, it could tell other telescopes, X-ray, gamma ray, where to look. There's no delay, no sending the alert down to Earth and back up. You could catch the afterglow right at the beginning. Data we lose now. A mission like that would change how we see the radio sky. It opens a new window. Not just on fast radio bursts, but on all the other brief, mysterious signals. We'd stop listening through a keyhole. We'd open a door. The signals are out there, telling their short, violent stories. To hear them fully, we might have to go, to leave home. All that data, it has a weight to it. Every new telescope, every survey like CHIME, they're not just collecting signals. They're creating a flood, petabytes of it, an ocean of ones and zeros, and at that scale, the questions you ask, they shift. They become questions of responsibility. Who gets to listen, and what's the cost? Finding these flashes is a big data operation now, and that means new considerations. Access is one. The most powerful telescopes, the fastest computers, they're in just a few countries. But the sky belongs to everyone. So how does a scientist somewhere else, with great ideas but not the same resources, how do they join the search? That's why things are moving toward open data. Shared archives, putting the raw data out there for anyone with tools to use it. That opens up discovery. It means the next big idea could come from anywhere. And it's not just about being fair, it's about using all of our curiosity. More inclusive science is stronger science. It means the story of the universe gets shaped by more voices. Then there's the physical cost, the environmental one. Processing all that data takes immense computing. Data centers running non-stop, using power, making heat. Astronomy's carbon footprint is a real concern now. The field knows this. There's a push for renewable energy for these centers, for smarter algorithms that need less processing, for building in places with natural cooling. The goal is to lessen the impact of looking up, so we don't damage the planet we're looking from. It's a balance. Our reach out there and our duty right here. And as artificial intelligence does more of the work, sorting the noise for those millisecond needles, new ethical questions come up. When an AI flags a burst, who gets the credit? The people who wrote the code or the scientists who make sense of it? And more than that, these systems can't be black boxes. Their methods have to be reproducible. We need to see why the AI made a choice, to avoid hidden biases in the code, to be sure what it found is really new and not just something from its training. The integrity of the discovery depends on that. This whole shift, it's not a side issue. It's the field growing up. It's realizing that understanding the universe isn't just a technical problem. It's a human project tied into our society and our environment. To grow the right way, astronomy has to look inward too. It has to build systems that are open, sustainable, fair, because the goal isn't just to decode the messages from the dark. It's to make sure everyone, everywhere can hear them. A signal from 1 billion years ago is a message. It doesn't have words, but it says a lot. A fast radio burst is a time capsule. It left its galaxy when Earth was young, when the continents were still forming. And it traveled across epochs. By the time that faint whisper gets to our telescopes, the galaxy that sent it might be gone. It might have merged or faded. We're not seeing the universe as it is, we're seeing it as it was. We're archaeologists, but of the present moment, sifting through ancient light. That time delay changes your perspective. We're not just watching a static cosmos, we're in a conversation across time, listening to echoes of violence and transformation that are already ancient history. The randomness of these bursts, the unpredictable moment they flash, that echoes something else. It echoes the universe's fundamental nature. It's not a placid clockwork machine. It's a dynamic system, a chaotic one, where brilliant catastrophes are just a regular feature. These millisecond screams are a reminder. Creation and destruction are two sides of the same coin, woven into deep time. Our long struggle to understand them, that mirrors an older story. It's the story of finding patterns in the noise. Our ancestors looked at scattered stars and saw constellations. They saw myths, guides for navigation. We look at scattered radiostatic and see fingerprints of magnetars, maps of missing matter, the structure of the cosmic web. The tools are different, but the impulse is the same. To listen to the void and hear a story, to take the chaotic and find meaning inside it. That quest shows a specific kind of ingenuity. It's not just about bigger telescopes, though that's part of it. It's about building better questions. It's about the patience to sift through decades of data for a 5-millisecond anomaly. The humility to chase a ghost for years, find out it was a microwave oven, and then press on. The collaboration that turns one observation into a global dialogue. The story of fast radio bursts is a story about how we learn. It shows our capacity for wonder, our resilience facing mystery, our drive to push the boundary between the known and the unknown. In the end, these signals from the void, they do more than teach us about neutron stars or intergalactic gas. They hold up a mirror. In our effort to decipher them, we see our own reflection. A species curious enough to build ears that can hear the universe's shortest stories, and persistent enough to spend a lifetime trying to understand them. They reaffirm a simple idea: we are part of this cosmos, not separate from it, and by trying to comprehend its most fleeting whispers, we are, in a small way, learning to comprehend our own place. Our place within its immense and unfolding narrative. Looking for these flashes means looking for patterns in the noise. To catch a millisecond signal in all that data, a big dish isn't enough. You need a brilliant filter. That's why the search for fast radio bursts has turned into a kind of laboratory. It's where the ancient study of the stars meets the modern art of the algorithm. The raw signal from a telescope is just a chaotic river. There's the hum of Earth, the crackle of the sun, the hiss from the cosmic background, and somewhere in there might be one unique ripple. A ripple that lasts 5,000ths of a second. You can't find that by eye, so scientists write code. these software pipelines act like digital sieves. They process the data in real time, applying mathematical filters. They're looking for a specific signature, a signal that's dispersed, arriving at different frequencies at slightly different times. These pipelines have to be incredibly smart. They have to ignore all the false alarms, the radar from airplanes, bursts from satellites, even microwave ovens that fooled people once. It's a classification problem, and it's perfect for machine learning. Researchers train neural networks on millions of samples of real data. They show the system what a real burst looks like, and 10,000 examples of what it doesn't look like. The algorithm learns the subtle differences. It learns to recognize the fingerprint of a cosmic event in all that terrestrial noise. Over time, it gets better than any human could at making that split-second call. This fusion is creating a new kind of researcher. The modern radio astronomer is often as fluent in Python as they are in the physics of neutron stars. Their toolkit includes databases, statistical inference, cloud computing. They might spend a morning tweaking a deep learning model to find burst candidates, and their afternoon using that output to theorize about magnetic fields in a distant dwarf galaxy. This shift is driving innovation beyond astronomy. The techniques developed to find these faint signals are being adapted for other fields. The same algorithms that sift the radio sky for a fleeting burst can look for patterns in medical imaging, monitor seismic activity in sensor networks, or detect anomalies in financial markets. The challenge of the data itself forces new methods into being. When you have petabytes of information to search, you can't just look harder, you have to look smarter. You have to invent new ways of seeing. So the story of fast radio bursts isn't just written in the light from distant galaxies anymore. It's written in lines of code, in the architecture of neural networks, in the hum of server farms processing the night sky. The mystery is being solved not only with mirrors and lenses, but with silicon and logic. This partnership shows something about our era of discovery. To understand the universe's greatest secrets, we first have to learn to master the oceans of information it creates. We have the engine, we know where it is, but that final piece, the exact sequence inside that millisecond, it's still a black box. How does it take all that pent-up magnetic energy and focus it into a radio scream so brief it's over before you can blink? The efficiency is baffling. It's like a lightning bolt draining an entire ocean of electrical charge in a single flash. The scale is just that extreme. Think of the Magnetar's surface. It's a crust of iron nuclei locked in a lattice under immense pressure, and above it, a magnetic field so intense it warps the shape of atoms. That creates a constant tension, like twisting a rubber band tighter and tighter. Eventually, something gives, the crust cracks, a starquake, but the quake itself isn't the burst. It's just the trigger. The real action is in the magnetosphere, that cage of magnetic force lines around the star. One idea is magnetic reconnection. Picture those field lines as elastic bands, stretched and tangled by the quake. When they snap and reconnect, they release a catastrophic amount of energy. It's the same process that powers solar flares, but here the field is a quadrillion times stronger. The reconnection would blast electrons and positrons outward at nearly light speed. As that fireball plows through the surrounding plasma, it could generate a shock wave, and that shock wave, rippling through the chaos, might be what emits the coherent pulse of radio waves we see. Another possibility focuses on the crust itself. The quake could shake the magnetosphere like striking a bell. That vibration could accelerate particles, creating a sudden beam of radio emission. Or maybe the quake opens a crack, allowing a blister of superheated plasma to erupt from the interior into the magnetosphere, triggering the blast. The challenge is the timing. All of this, the crack, the reconnection, the acceleration, the emission has to happen and be over in less than 5 milliseconds. From our view, it's a single event. But inside that window, there's a universe of physics. Which step is the bottleneck? What dictates the burst's exact duration, its substructure? We don't have a complete simulation that can start with a stressed magnetar and reliably produce a synthetic fast radio burst that matches all the quirks of the real ones. This is why more detections alone won't solve it. We need the burst that breaks the model, the one with a signature so strange, so detailed, it rules out every current theory except one. It might be a burst with an impossibly clean polarization pattern, pointing to a shock wave in a perfectly smooth magnetic field, or one preceded by a specific X-ray flicker, a sign of crustal movement milliseconds before the radio flash. Each new, peculiar burst is a clue, a constraint that helps refine the virtual models, stripping away possibilities until only the true mechanism remains. The hunt is no longer just for the source, it's for the signature of the process itself, hidden within the fleeting geometry of light. 2007 is where it starts. That's when the Lorimer Burst was found. It was in old data, but they finally saw it. It was proof the universe could do this, it could make this kind of signal. But after that, for years, it was just that one, a single event, a strange thing out there. Then 2013 changed that. By looking at how the burst was stretched, its dispersion, they showed it came from outside our galaxy. It had passed through intergalactic space, so it wasn't local. It was from a huge distance, and that meant the source had to be incredibly powerful. It turned it from a curiosity into a real mystery. The next big moment was 2016. That's when Arecibo saw one that repeated. FRB 121102, the repeater that changed everything, because if it repeats, you can't be looking at a one-time explosion. It has to be an engine, something that survives, and with a repeater you have a location. You can go back and look. Things moved faster after that. Then in 2020, we got an answer from much closer. A burst came from inside our own galaxy, and it came from a known magnetar, SGR 1935 plus 2154. It had a starquake. That was the first direct link. We didn't have to guess anymore. There was the source right there, a magnetar, a natural engine, so each of these steps did more than just add a piece. They closed off whole ideas. The repeater meant not all bursts were from things blowing up once. The magnetar gave us a real model, a physical blueprint. It's not just a timeline of dates, it's how understanding actually shifts. You start with a blip in some data, and it becomes a whole field. The pace just keeps getting faster. New chapters are coming all the time. History teaches us something. Every time we build a better window, the universe shows us something unexpected. The first telescopes found moons around Jupiter, and that broke the idea that everything went around Earth. Then radio astronomy came along, and it showed us pulsars and quasars, these objects with incredible power. The lesson is that our picture is always incomplete. Now we have the next generation of instruments, like the Square Kilometre Array. It's a window wider than any before. And with it will come new surprises. We should expect to see fainter fast radio bursts from greater distances, pushing our sensitivity. We might catch bursts that last longer, not milliseconds but seconds. That would hint at a different kind of engine, or we might find their properties linked to other mysteries. A burst that arrives at the exact same moment as a peculiar gamma-ray flash. That would connect two puzzles into one, or a one-off burst, and its location lines up perfectly with a ripple in space-time, a gravitational wave, that would tell us we just heard and felt the same catastrophic collision from across the cosmos. These connections would change everything. They would weave separate threads of astronomy into a single, richer picture. To get ready for that, the field has to stay agile. Theories can't become dogma. The story of the Puritans and the microwave oven taught us that humility. The discovery of the repeater taught flexibility. Scientists have to be ready to let go of a favored idea if the data demands it. The whole infrastructure of discovery, the alert networks, the open data, the global collaborations, it's all built not just to confirm what we think we know, but to capture the next anomaly. The next big surprise isn't a matter of if, but when. It's likely sitting in a data stream right now, a faint whisper in the static, waiting for the right algorithm, the right pair of eyes to see it for what it is. A signal that doesn't fit, a pattern that breaks the mold. It will challenge our comfortable assumptions all over again, and that's the most exciting part. Because in that moment of confusion, in that struggle to make sense of the new and strange, that's where we truly learn. That's where the universe gets to tell us its next story. That first signal was just a blip in old data. The Lorimer Burst. It could have been ignored, but it wasn't. It started a search. We had to build better telescopes. We had to write new software. We had to work together across borders. There was that false signal from a microwave oven. Then we found the first repeater. That gave us a location, and then we heard a magnetar in our own galaxy. That was confirmation, a source we could point to. Now we use these bursts. They weigh the universe's missing matter. They map magnetic fields in empty space. The story is about the search itself, the persistence, the collaboration, making sense of the noise. We think magnetars are the cause. But we don't know for sure. Are they the only cause? The one-time bursts might be different, more final. The physics of how a magnetic field snaps to create that radio scream, we're still figuring that out. With simulations, with each new signal, new telescopes are coming. Like the square-kilometer array, there will be a flood of new data, new patterns, new outliers. It will challenge what we think we know. The story isn't finished.